In this paper, we propose a sample-efficient approach for training language-conditioned manipulation policies that allow for rapid transfer across different types of robots. We introduce two complementary methods, namely supervised attention and hierarchical modularity. We also show that the learned submodules can be used to introspect the robot decision-making process. Given a natural language instruction by the human user, the method generates corresponding robot controls. In doing so, it takes into account the current visual feed from a camera as well as the robot proprioceptive data. Here we see another execution of the human instruction provided in free form from natural language. Due to its modular nature, our method is able to transfer policies across different robots. Using a policy pre-trained on a Canova robot, we are able to transfer the policy to a UR5 and Franco robot with 320 demonstrations. Our method is also able to transfer from simulation to real-world robots. In order to achieve data efficiency, we introduce two innovations, namely supervised attention and hierarchical modularity. Supervised attention is a training objective that can incorporate human prior knowledge of optimal query key pairs into attention neural networks. If we know which key tokens are important for the queries to look at, we can treat the similarity score as a maximization goal. One of the supervised attention objectives in this paper identifies image patches that contain objects of interest. As shown in this scene, the agent is able to focus attention on the target object during runtime. Using supervised attention, we can train attention layers that can focus on specific input variables of interest. In turn, we can use this mechanism to train submodules within a neural network. The submodules implement components of the overall task. In case of manipulation, these components may perform subtasks such as detecting the end effector or identifying the target object within the language instruction. The subtasks, which are assigned to submodules embedded in the attention layers, are further arranged in a cascade fashion, with the output embeddings of one module being the input to the next module. Incorporating the mentioned innovations, we're able to achieve an overall 82.4% success rate on the three tasks when trained on 1,600 demonstrations. Our method is also able to provide an introspection of the decision process by querying the submodules at runtime. In this scene, the blue circle is the predicted target object, the red square is the predicted end effector position, and the green area is a visualization of the attention map. All values displayed are generated from a single neural network. Language-conditioned policies, trained with our approach, can recover from human perturbations. In this scene, we deliberately move the soda can to another place. In a closed-loop fashion, the robot is able to adapt to a new visual information and generate controls to grasp the soda can again. Our method generalizes to a variety of untrained language expressions, synonyms, and descriptions. In this particular case, we use delicious sourdough to refer to the bread. Various limitations still remain. For example, trained models cannot identify objects through spatial reference, like the object next to Pepsi, or by their function, such as the object which contains milk. We also test our model's ability to add new modules to the existing hierarchy by incorporating an obstacle avoidance behavior during manipulation. To this end, a new module is included for detecting an obstructing obstacle. Thereafter, the robot is able to calculate the displacement between the obstacle and the end effector, and thus avoid collision with the obstacle. Thank you for watching.